or not 6. Starting with questions on assignment number 5.
So when we show that x, y, and a, b are a relation on Z, we have to we have to show that x and y and a and b are related. So then they can all be an element of Z.
The relation is on Z cross Z. Right? The relation is between pairs, x, y, and a, b. So x, y, and a, b are the same when the sum of the squares of the components are the same. But what's your question again?
Never mind. I guess I don't know. Thanks.
Right. I mean, but of course, when you take the pair and you square them, the components, you add them, then you get an integer. Right. So, like I was saying last time, now when you want to look at these equivalence classes, so like the equivalence class of 1, 0, that's the set of all x, y that's related to 1, 0. In other words, the x squared plus y squared is equal to 1 squared plus 0 squared is 1. Well, there's only a few integer points that actually satisfy that. X squared plus y squared equal to 1. For real numbers, of course, there's infinitely many. That's the unit circle, and that's all the coordinates of those points are the sine and cosine of whatever angle we're talking about here, but we're not talking about real numbers. Okay, we're talking about integers. So there's only just a few points for integers that lie on that circle. For the equivalence class of 1, 1, again, there's just a few points, integer points, x squared plus y squared equal to 2. Right, I mean, x squared and y squared are both positive numbers. Well, non-negative numbers. Non-negative numbers adding up to 2, well, there's either 2 and 0, but that can't be the case because x squared equal to 2 doesn't happen with the integers. Or 1 and 1. It must be 1 and 1. And then for the last one, the equivalence class of 3, 4, right, that's all the points x squared plus y squared equal to 25. Now, there's a few more integer points, but if you remember about the Pythagorean theorem, you'll know what those integer points are. Okay? And draw those on the circles they represent. Or, sorry, draw them on the circles, for all real numbers that satisfy these points. What else?
For number 4,
Mm-hmm.
I emailed you about that one yesterday. And I think you said something like, I was only showing one of the cases, and you have to show that it's either that or the other.
There's 2 cases. You have to pick. There's. So I mean, x1, y1 is less than or equal to x2, y2, possibly for 2 different reasons. This reason, or this reason. So you have to consider both. Right? So if it's for this reason, then here's the proof. If it's for this reason, then here's the proof. Just like we've been doing all along with multiple cases. Let me show you what I mean. So number 4. So for number 4, so right, x1, x2, right? So what is it? A is poset under relation. Well, not use that language. So less than or equal to sub A is partial order for A, and less than or equal to B is partial order for B. Okay, define x1, y1 less than or equal to x2, y2. So for A cross B, so we've got two partially ordered sets. A is a partially ordered set, and B is a partially ordered set. We don't know anything about them. Just they are partially ordered sets. Okay, so now we're going to define a partial order, we're going to define a relation on A cross B. Define x1, y1 less than x2, y2 when either x1 is less than x2 or x1 equals x2 and y1 less than or equal to y2 in the partially ordered set B. So there's two possibilities, right? I mean, that's one thing that it could be, and that's the other thing that it could be. You know, where this means that x1 is less than or equal to x2 and x1 is not equal to x2. So that's what that symbol means. x1 is less than or equal to in A, x2, and x1 is not the same as x2. All right, so now for antisymmetry, what's the assumption? So assume what?
x1, y1 less than or equal to x2, y2, and x2, y2 less than or equal to x1, y1.
Mm-hmm. So by definition, what? Definition is right there. It's right here. So apply the definition to this one.
It's whatever that is, that what you just stated above.
Say it. Say it now. Say it.
x1 is less than x2 on A.
Uh-huh.
And
or
x1 equals x2 and y1 less than or equal to y2 on B.
Right. It's important to you know, say things out loud. You know, say those definitions. Say them out loud. Hear them when you're talking. I mean, you know, don't talk to yourself. I'm not advocating for that, but you know, explain what's going on verbally helps you to think. So by definition, this or this. Okay, well, if x1 is less than x2 in the partially ordered set A, then by definition, right, same thing here, right? Either x2 is less than x1 in A, or x2 equals x1 and y2 is less than or equal to in B, y1. Alrighty. Right, so first we apply the definition to this, and that tells us you either have this or you've got this. Right, so first we start with this possibility, and then we apply the definition to this second relation. And I hope you can see that that's not possible. If x1 is less than x2, it is not possible for x2 to be less than x1. Right, nor is it possible for x1 to be equal to x2. Right, so that case actually doesn't happen. Right. So anyway, so finish the proof from there. And then the second case, if x1 equals x2 and y1 less than or equal to and be y2, then by definition what does that mean? One of the situations will be impossible, the other situation works out and gives you what you want. Right? Whenever there's two possibilities, you must consider both. Typically, you consider them separately. Sometimes you can consider them together. Whenever you have an or, either this is true or that is true, you must consider this, and then you must consider that. And those are separate proofs, right? See what I'm saying?
Makes a lot more sense now.
Now, sometimes you can actually consider them at the same time, and it is possible in this case to do so. If you want, you can do it that way. Okay, so because this definition involves the or, there's more casework to be done, the separate casework to be done, right? Either you got this or you have that. So that gives you two cases right away. But then this relation gives you another two cases. So there's 2 times 4 is actually 4 cases. Not all of them are possible because you can't have that x1 is less than x2 and x2 is less than x1. That's not possible. And so actually only one of them is possible, and you see which one it is. And that's the one when they're actually the same. All right, what else, guys? Anything?
For number 3, the NK equals L, or NL equals 1.
Yeah.
And the natural number, so what you're saying in that is, in the natural numbers, NL equals 1 only if N equals L equals 1, right?
Yeah, there's no proof necessary. We're talking about the natural numbers, right? I mean, I'm assuming you all did your times tables when, you're in 3rd grade, but this is the thing to be thinking about. Let's write it out. So not the timetable up to 12 or whatever they're teaching nowadays. They still do it up to 12, at least when you guys were kids. They did it up to 12 when I was a kid. All right, so you've got the numbers 1, 2, well, you got 0, but we don't have to worry about 0. 4, 5, 6, 7, 8, so on and so forth. 1, 2, 3, 4, 5, 6, 7, 8. Those are the natural numbers, and we're talking about multiplication in the natural numbers. All right, 1 times 1 is 1, times 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 4, 6, 8, 10, 12, 14, 16, 6, 9, 12, 15, 18, 21, 24, right, so on and so forth. Here's 1. Okay, things only get bigger as you go down the table, right? 1 only appears there in the multiplication table for the natural numbers. Right, so in the natural numbers, a times b equal to 1 implies a equals b equals 1. That's it. There's nothing to say. I suppose you could give a proof, but it's not necessary. I mean, of all the things that we can assume everyone knows arithmetic. Unless there's something like really tricky that you need to mention. Now, of course, this is not true outside of n, right? This isn't true, right? In Z, for example, a times b equal to 1 implies what? For the integers.
A and B both equal 1, or A and B both equal -1?
In the real numbers, in the real numbers or in Q, a times b equal to 1 has infinitely many solutions. Right, it's the
A equals 1 over B and B equals 1 over A.
Yeah, the hyperbola, right? This hyperbola here. But we're not dealing with that. We're just in the natural numbers. So just in the natural numbers, just a times b equals 1 means a is equal to b is equal to 1. That's it. In the multiplication table, stuff only gets bigger as you go down the multiplication table. So 1 only appears there. Right? All right. So we can do some questions again on Friday. Let's go back to chapter on induction. So again, given a domain of integers, consecutive integers, with a smallest member, so with a starting point. So consecutive integers with a starting point. So like the natural numbers, 0, 1, 2, 3, 4, so on and so forth, or something like this, -2, -1, 0, 1, 2, 3, 4, so on and so forth, or anything else like that. Mathematical induction is used to prove true over D statements of the form for every n, P of n is true. Here, P of n is a predicate. Okay. Again, usage of predicate logic notation within the proof is not really done. But in order to explain induction, really, like to explain it well, you need to have the language of predicate logic to explain it. So to show for all n, P of n is true over this domain, starting at 1, 1, 2, 3, 4, so on and so forth, it suffices to show that P1 is true. And for every n, Pn implies Pn plus 1. That's true as well. So why does that work? Given that P1 is true and then P1 implies P2 for every n. For every n, Pn implies Pn plus 1. In particular, P1 implies P2. Well, if P1 is true and the implication is true, it can't be that P2 is false. So P2's got to be true. But then given that P2 is true, and then for every n, Pn implies Pn plus 1, we have to have that P2 implies P3 is true. But because the hypothesis P2 is true, we can't have that the conclusion is false. So P3's got to be true. given P3 and P3 implies P4, you get that P4 is true, so on and so forth. It just keeps going like that.
Kind of like a staircase.
Yeah. So that inference rule is called, you don't know, maybe you know. It's called modus ponens. So it's the basic rule of deduction in logic. Given A and A implies B are both true, these together imply that B is true. Right? You're all students in my class, and you're a student in my class, and then if A is a student in my class, then he's a student at Wright State. Therefore, you are a student of Wright State. Right? That's the basic rule of deductive reasoning. Modus ponens. And then there's the variations on that. B naught and A implies B being true gives you that A naught is true. Things like that. All right, but that's not what we're talking about. I just want to at least mention it. So how do we use it? That's the more interesting aspect of things. And then we did this one from last time. So the sum of the odd numbers, 1, 3, 5, 7, 9, all the way up to 2n minus 1. So the sum of the first n consecutive odd numbers adds up to n squared for every n bigger than or equal to 1. So in this problem, P of n, the predicate P of n, is this statement of equality. That statement of equality is either true for a given value of n, or it is false for a given value of n. What we're going to show is that that given predicate is true for every n. Okay? So like for example here, P of 4 means this, the sum of the first 4 consecutive odd numbers, 1, 3, 5, 7. That's equal to 16, right? Which is 4 squared. So that's true. Okay, so we start with the base case. Show that P of 1 is true. Again, P of n is that statement. So what's P of 1? P of 1 is, well, the sum of the first n consecutive odd numbers. Well, when you're talking about the sum of the first n consecutive odd numbers, that's just 1 by itself when n is 1. And then n squared when n is 1. So they're the same. Okay, great. So P1 is true. That's the base case. Usually the base case is easy, although not always. Inductive step. So Pn implies Pn plus 1. So in the inductive step, you need to write out, normally you do it by direct proof. So normally it's done with a direct proof rather than contrapositive or contradiction, although it could be done that way. It's not so common. So you must assume the hypothesis is true, assume Pn is true, and then show that Pn plus 1 is true. Okay, now in doing those assumptions, you must write them out explicitly, especially the hypothesis, the induction hypothesis. The induction hypothesis is that Pn is true. 1 plus 3 plus 5 up to 2n minus 1 is equal to n squared. That is true for some n in the domain that we're talking about. Right, I know we're showing this. We're showing for every n, Pn implies Pn plus 1. Right? But you're not assuming that this is true for every n. You can't assume it's true for every n because that's what you want to prove. You can never assume your conclusion is true. Okay? So we're just assuming that Pn is true for some arbitrary n. Arbitrarily chosen n. It's arbitrarily chosen, but it's still a single thing. Right? Arbitrarily chosen, but it's still a singular thing. So 1 plus 3 plus 5 plus 2n minus 1 equals n squared. That's true for some n. That's called the induction hypothesis, the hypothesis right here. And then this is the target conclusion. Show that Pn plus 1 is true. What is Pn plus 1? This is Pn. So substituting n plus 1 for n, you get that. That's Pn plus 1. This is Pn. This is Pn plus 1. So you assume the Pn is true. That's your induction hypothesis. And then you state explicitly your conclusion. Okay, this induction hypothesis, that is the standard term for this hypothesis. Target conclusion is, I'm sure someone else has thought of it in some times past, but that's just something I call it for pedagogical reasons. All right, so how do you show that this equality is true? You start on the left-hand side of the equation. You work your way over to the right. Okay, 1 plus 3 plus 5 all the way up to 2n plus 1. So that's the first n plus 1 odd numbers. Which odd number comes right before 2n plus 1? Well, it's 2n minus 1. So this sum can be written more specifically like that. 1 plus 3 plus 5 up to 2n minus 1 plus 2n plus 1. Well, we assumed that this sum here, we assumed that that's equal to n squared. So this can be replaced by n squared. Why? That's the induction hypothesis. And you must state when you use the induction hypothesis explicitly. Okay, so this expression here is equal to n squared plus n plus 1 because we assumed that this is equal to n squared right here. What is that thing called? The induction hypothesis. Okay, so that's equal to n squared plus 2n plus 1, which is equal to n plus 1 squared, and we're done. That's what we wanted. Nice first application of the principle of mathematical induction. First principle of mathematical induction. Side note, this statement can actually be proven without using mathematical induction. It has a geometric proof. Of course, n squared is the number of dots in an n by n array, but then when you look at the array and you group the dots like this, you see that the number of dots is consecutive odd numbers. That's 1 dot, 3 dots, 5 dots, 7 dots, 9 dots, so on and so forth. So the sum of the first 5 consecutive odd numbers is a 5 by 5 array of dots, which is 25 dots. Now, not every statement that you prove by induction is going to have some nifty geometric proof or something like that. In general, if you can prove something without induction, it's sometimes considered better because you have more of a, it gives you more of a, it's more descriptive. I mean, this is more descriptive than the inductive proof. But anyway, that's just for enrichment. How about this? Okay, so for tomorrow, or for next time, please do this. Give yourself 10 minutes and give it a shot. So for next time, prove that 1 plus 2 plus 3 plus, so the sum of the first n integers is equal to n times n plus 1 over 2 for every n bigger than or equal to 1. So use induction to prove that. So now we'll do the following. As another example. Okay. So give that one a shot yourself for Friday.
I've seen it before.
Yeah, I'm sure. Then this one can be proven without induction as well. Give that one a. I mean, for those of you who haven't, give it a try and write out that proof. All right. So here's another example. So you probably saw this in calculus because they actually use that in Calc 1. So let's prove that 1 squared plus 2 squared plus 3 squared all the way up to n squared is equal to n times n plus 1 times 2n plus 1 over 6. Show that that's true for all n bigger than or equal to 1. Okay, so So now here, Pn is this thing right here. So Pn is that statement, that equality there. That equality is either true or it is not for a given value of n. We are going to prove that it's always true. All right. Base case, n equal to 1. All right, well, when n is equal to 1, 1 squared plus 2 squared plus 3 squared, all the way up to n squared is actually equal to what? So it's the sum of the squares of the first n consecutive integers. Well, when n is equal to 1, that's just what does this mean?
1.
Just 1. 1, this thing means just 1. And then n times n plus 1 times 2n plus 1 over 6. When n is equal to 1, well, that's 1 times 2 times 3 over 6, which is 1. And these are the same. Right? They are equal. So P1 is true. Inductive step.
So for the base case, you just have to provide an example.
Well, the specific example for n equal to 1 or wherever else you're starting.
Yeah, okay.
Whatever your starting point is. Yes, exactly. Inductive step, Pn implies Pn plus 1. Okay, so inductive hypothesis. Assume that 1 squared plus 2 squared plus 3 squared plus n squared is equal to n times n plus 1 times 2n plus 1 over 6 is true for some n bigger than or equal to 1. So some arbitrarily chosen n. And then we want to show that Pn plus 1 is true. Well, Pn plus 1 comes from Pn by replacing n with n plus 1. So this becomes 1 squared plus 2 squared plus 3 squared all the way up to what if I replace n with n plus 1?
N plus 1 squared.
Yeah, just n plus 1 squared is equal to, and this becomes, well, n plus 1 times, what's this? So n plus 1 becomes, and simplify it if you can, becomes
N plus 2.
n plus 2, and then 2 times n plus 1 becomes 2n plus
2.
So this is 2n plus 1, and we're going to replace n with n plus 1. So it looks like that, which is what?
2 times n plus 1 plus 1.
Gotta distribute the 2 here.
2n plus 3.
2n plus 3. All right, so this is 2 times n. So when you replace the n with n plus 1, 2 is still multiplied by that whole expression. All right, so it becomes 2n plus 3. You all okay with that? All right. 2n plus 1, replacing n with n plus 1, you get 2n plus 2 plus 1. Right, it's 2 times n plus 1, which is 2n plus 3. So we want to show that this is true as well. Okay, well, 1 squared plus 2 squared plus 3 squared plus n plus 1 squared is equal to, well, what comes right before n plus 1 squared? What comes right before n plus 1 squared? What's the term right here?
N squared.
N squared. Well, the sum from 1 squared to n squared is equal to what?
N times n plus 1, 2 plus 1 divided by 6.
Yeah. And then this is still there. Why? Is that true? What's the reason for that?
Inductive hypothesis.
The inductive hypothesis. The assumption that you make at the beginning of the inductive step by the inductive hypothesis. All right, so now let's do some algebra here. Well, I have a common factor of n plus 1, so I'll factor that out. And now I'm left with n times 2n plus 1 over 6 plus n plus 1. So that's equal to n plus 1 times 2n squared plus n plus, I just need to lower that. Uh, 2n squared plus n over 6 plus, this one becomes 6 times n plus 1 over 6, which is n plus 1 times, so now this becomes 2n squared plus 7n plus 6 over 6. Well, 2n squared plus 7n plus 6, lo and behold, if you factor it, is equal to 2n plus 3 times n plus 2 over 6, right? 4n plus 3n, 7n, and 3 times 2 is 6. And that's the factorization of that. So that's equal to n plus 1 times n plus 2 times 2n plus 3 over 6 as required. All right. This one has a geometric proof, although it is not any easier than this. And there's an algebraic proof for these things, which is really clever, but that's a more advanced topic, algebraic proof. So actually, there is a theorem of this sort for, this is the sum from 1 to n. This is the sum from 1 squared to n squared. Then the sum from 1 cubed to n cubed, 1 to the 4th to n to the 4th. They all have a nice polynomial expression like that. But that's a topic that you would do in combinatorics and graph theory. That I would cover anyway. It uses it's an algebraic proof, but it uses a discrete version of calculus, which is pretty cool. All right, let's see. Here's another example. So these were equalities. Let's look at an inequality. So let's show that n factorial is greater than 5 halves to the n minus 1 for all n bigger than or equal to 4. Okay, so before we get into that proof, let's just look at quick review about n factorial. I mean, y'all have seen it before, I'm sure. But, here's an interesting property of n factorial. Remember, n factorial is equal to n times n minus 1 times n minus 2 times ... 3 times 2 times 1. So therefore, n plus 1 factorial is equal to n plus 1 times n minus 1 ... 3, 2, 1. All right, what's this here?
N factorial.
It's n factorial, right? So n plus 1 factorial is equal to, in general, n plus 1 times n factorial. So this is going to be useful in doing an induction proof on a factorial expression. Okay? All right. Now here Pn is this guy here. This is Pn. And notice that we're proving Pn for all n bigger than or equal to 4. That's because, like, P1, 2, and 3, those are all false. All right, P1, so note, by the way, P1 is equal to the statement that 1 factorial is greater than 1, right, which is false. P2, which is equal to 2 factorial, right, is greater than 5 halves. Right, 2 factorial is 2. 5 halves is 1.5. That's false too. P3 is the statement 3 factorial is greater than 5 halves squared. That's 25 over 4. 25 over 4 is what? Is 6 point something, right? So this is 6. 3 factorial is 6. 25.4 is 6 1/4. Right? It's still false. Right? It doesn't become true until n equal to 4. And then it's true after that. Right? By the way, 25 over 4 is equal to 6 plus 1/4, right? It's just total tangent now, but just something that, perhaps you haven't, like, sat and thought about it yet, but maybe perhaps you have. 25 over 4, that's 6 plus 1/4, right? Is this correct, what I wrote?
Yeah.
Yeah.
Yep.
So why do people write
'Cause-
that? That's not equal to this. That's right. That's equal to 3 halves. So why do people write this for 6 1/4 rather than that?
They just use mixed numbers maybe when they were younger.
Yeah, it's shorthand. I mean, everybody does it. Nobody writes this, right? I mean, except when you're doing formal arithmetic, you might use this. That's just a shorthand notation that has developed over the centuries. It's shorthand notation for for everything, aside from formal mathematics. Just something to be aware of. Okay, so that predicate Pn is not always true. In the previous examples, it was always true everywhere it made sense. Here, the predicate makes sense for P1 for n equal to 1, 2, and 3, but it's still false. So here, the base case is n equal to 4. Okay, so when n is equal to 4, right, n factorial is 4 factorial is 24. And 5 halves to the n minus 1, well, is equal to 5 halves to the third is equal to, well, let's actually plug that into a calculator. Oh, did I say? It's 2.5. I think I said it was 1.5 earlier. It's 2.5. Where's my calculator? There it is. 1.5. The third. So 3.375. 3.375. No, it's not that, sorry. 2.5. 15.625. $15.625, right? And we see that. I mean, 24 is indeed larger than 15.625. Right? All right, induction step. Okay, a few little twists on the inductive step here. So again, we're trying to show that Pn implies Pn plus 1. So assume that so what is the statement? N factorial is bigger than 5 halves to the n. 5 halves to the n minus 1. For what?
For all n greater than or equal to 4.
For some n.
Or for some, yeah.
Yeah, for some n in our domain. So the domain here we're talking about is n what? Bigger than or equal to
4.
4, yeah. Show that n plus 1 factorial is bigger than 5 halves to the n is true as well. Okay. Now, when working with inequalities, did we do this yet? Did we work with inequalities yet? We were working the partially ordered set thing. I forgot, did we do this? Anyway, so, no, we didn't. Okay. When trying to show an inequality is true, so, as I was saying before, when you're trying to show an equation is true, typically you work in a string of equalities. Or like, when you were trying to show some propositional logic expression was logically equivalent to another propositional logic expression. We wrote, a chain of logical equivalences. Or in this case, a chain of equalities. Also with sets, we did that, right? A chain of sets. Set equalities, set identities. So this is equal to this, is equal to that, is equal to this, and that's what we wanted at the end. So the first thing is equal to the last thing, which is what we wanted. Okay? One does not do a proof of an equality by stacking equations. Right? Like how you would have done it like in your trigonometry class in high school. Okay? That's not done that way. It's done in a string like that. Okay, it's simply not written using stacks. I don't know why they still insist on teaching it that way, but they do. It's not wrong to do it in a stack, but it's definitely less elegant and it makes less sense. All right. That said, with inequalities, you must work in a string. You cannot stack inequalities and hope that it makes sense. It simply won't. Okay? You have to work in a string of inequalities. You have to say this expression is equal to that expression, is bigger than that expression, is bigger than equal to this expression, is greater than this expression, is equal to this expression. Therefore, the first expression is greater than the last expression. So you got to work in a string of inequalities all pointing in the same direction. That's clear. Okay, you can't do A is equal to B and therefore A is greater than C. Why? Why would that be true? Right? And therefore D is greater than C and therefore F is greater than or E is greater than F. I mean, why would A equal to B imply A is bigger than C? Why would it? It could, but why does it imply that? Well, it would imply that if B was bigger than C. Right? But if B was bigger than C, why didn't you just write A is equal to B is bigger than C? Why stack it like that? Right? Because you're going to have to say why in between here. And then why would D be bigger than C? Because D is bigger than A? Or for some other reason. And for that matter, why would E be bigger than F? Right? I mean, here, you know, there is a reason. Here, is D bigger than A? Maybe it's not. If it was, why didn't you start with D? It just does not make sense to stack inequalities. They must be done in a string. Now, sometime that string will have a substring, like the reason for this one, you might write it down here, and that's totally fine, but the overall thing needs to be a string with inequalities. Okay, so we're trying to show, okay, that n plus 1 factorial, well, like we were saying before, that's equal to n plus 1 times n factorial. What do we know about n factorial? What does the inductive hypothesis give us here? Well, we know that n factorial is bigger than 5 halves to the n minus 1. Right? N factorial is bigger than 5 halves to the n minus 1. So if I have a multiplier here, a times n factorial is bigger than a times 5 halves to the n minus 1, as long as it's positive, which n plus 1 is. Right? So by the inductive hypothesis, this is bigger than n plus 1 times 5 halves to the n minus 1. And then, because n is bigger than or equal to 4, this is bigger than or equal to 5 times 5 halves to the n minus 1. Right, and 5 halves is strictly greater than 2.5. Well, it's strictly greater than 5 halves times 5 halves to the n minus 1, which is equal to 5 halves to the n, as required. That's that. Okay, so we started with the first expression, and we did equals, greater than or equal to, greater than, equal to. And because somewhere within that chain we have a strict greater than, we're good to go. We get that the first is greater than the last. Right? So proving an inequality is done as a string of inequalities, right, with the reason for each one underneath. Unless it doesn't need a reason, like 5 is bigger than 5 halves. Okay, so that's all for today. Give that one a go for next time, please. The one that I assigned for you up here. The consecutive integers, 1 plus 2 plus 3 up to n is n times n plus 1 over 2. Give that a go. And then we'll continue this next time. And please, if you have any questions on the homework, email it to me and I'll look at it for you. Okay. All right. Have a nice day, everybody.